So I'll get you to start on this exercise straight away. Last lesson, what we looked at, the idea of we had a falling object who experiences two forces, weight force pulling it down towards the ground due to gravity, and then we had force shoot air resistance in the opposite direction, pushing it back up. And at some point, speed of the object's getting faster and faster, and then at some point, those two forces balance each other out. And at that point, the object reaches its terminal velocity. It's the most largest maximum velocity. So we can rearrange for that velocity from the formulas for force, and we get this expression.
Building up the
So that
night,
becomes
taking
the
people on a
useful to
journey,
calculate
instead
the
of
terminal
just
velocity
banging
of
out
the falling
for
object.
1 hour. So that was so much fun for
So I'll
me,
get
and what I
you to
did
just,
today in this Go On Air show,
think
I tried
about
to put a
information
bit
in this
of everything
question
together
and
to give you a nice recap of my
have
Australian
a
tour.
go at
We kick off with
find that
Sydney.
formula and see if you can
That
get a
was
calculation
Marquee.
for the terminal velocity.
Welcome to Go On Air.
Very good. 17.2. Who has got something similar to 17.2 meters a second? A little bit different? That's all right. Let's just check to see what we would get. Now, let's identify some of the key parameters. M refers to mass. Very good. So we talk about a mass of 80 kilograms. Opens his parachute, has a drag coefficient. There we go. So for the shape of an open parachute, that shape is like a hollow hemisphere. Yeah, half the sphere that is hollow on the inside. So the air goes in, gets captured by the parachute. Okay, so that creates a drag that can be measured with this coefficient of 1.8 as a factor. Okay, now forms a hemisphere of radius 7 meters. So the area that is experienced, that is observed from a cross section, from the point of view of the air molecules rushing past, that's just a circle. So you're looking at the area of your circle, pi r squared. Okay, now all this needs to be in meters, so we would have a 7 squared there as part of the area calculation. So calculate the terminal velocity of the skydiver. Well, the other quantity we need to have is our acceleration for gravity. 9.81 or 9.8 is fine, meters per second squared. And then the density of air, which is 1.25 kilograms per meter cubed. So a cubic meter box of air will weigh 1.25 kilograms. So using quantities like that in our calculation, we would get this overall amount of calculation you have to set up. Okay, and remember to do the square root. So just check your calculation on the way you did it. Compare it to this one and see if there's any difference. Did you identify which part you think was different? Okay, so the area part, yes. So the area is, in this case, you've got to think, what's the three-dimensional shape described? It's a hemisphere, and if we cut that in half and look on the side, you look at the flat surface, you go, oh, that's a circle. Okay, circle in shape. So we just want that area, that cross-sectional area. Alright, any questions? So in other words, 2.1 meters per second is the maximum velocity the skydiver will experience as he travels towards the ground. Okay? Even if he is still traveling over a large distance, he won't be speeding up any more than that. Yes? Yes, because this is a terminal velocity. This is the way we calculate the speed of travel, yeah, not an acceleration. Okay?
So only acceleration.
So when he's traveling at his terminal velocity, what would be the skydiver, the parachuter's acceleration towards the ground? Do you think?
Why not? Gravity's
Yep. So, and that's correct in the terms of the fact that if the weight force was the only force experienced by the skydiver, then he'll be accelerating at 9.8 meters per second squared towards the ground. But that weight force is balanced by the force chute air resistance, which reduces the overall force on the skydiver to 0, which means its acceleration will be also 0. 0. Because the net force, Newton said that the total net force is equal to mass times the acceleration. Yes? So if he's at terminal velocity, if the net force is balanced and reduces to 0, that means the acceleration must also be 0. So the acceleration is 0 because he's traveling at the terminal velocity, and what's special about the terminal velocity, it's a constant velocity. It's constant number. It doesn't change. There's 0 acceleration. Okay, any questions, please? Anna, if you had a question, mate, what was your question? Did it seem to match? Yeah, very good. Yes, Ashley. Sure, because the terminal velocity on a different planet would depend, for the same mass of 80 kilograms skydiver that has the same parachute of 7 meters in radius, okay? The terminal velocity achieved on a different planet with a different gravitational pull will depend on that, on its field, on its strength of its gravitational field. No, because this terminal velocity is what's achievable on Earth, and it requires the Earth parameters. That is, the gravitational field strength for Earth, which is 9.81, and the density of the atmosphere for Earth, which is 1.25 kilograms per cubic meter. But if we had done the same kind of activity on a different planet under a different atmospheric conditions and different gravitational field strength, you'll get a different achievable terminal velocity. Okay? No, that's 2mg, which is gravitational field strength of the planet. It's not got to do with the acceleration. It depends on the gravitational field strength of the planet. Okay? If you're on a different planet, you could achieve a different terminal velocity. Does that make sense? Anyone? Miguel? Yeah, the acceleration versus time graph, that's a very good question. So, the velocity versus time graph is what we saw at the end of last session. It rapidly increases, but then it becomes flat. Yeah? But now, the acceleration versus time graph, okay? Acceleration is the rate of change. Acceleration is the rate of change of velocity. So that is, we're thinking about the size of the gradient or the steepness of this curve at each point in time. Okay, so first off, it's rather steep at the start. So at the beginning of the journey, close to t equals 0, look how steep that curve is. Yep. So the acceleration value is a higher number, large number. Actually close to as high as, before the object starts moving, it's as high as 9.8. But then it decreases from 9.8 as the velocity increases. And it decreases down to, look how what the steepness happens to this curve after a while. So later on in the journey, the steepness is almost flat. In other words, it's reducing down to 0. So it will actually start to look like that. Okay, does that make sense? So in other words, the acceleration at the beginning of the journey, just as the guy jumps out of the plane or just as he turns on his parachute, yep, it is as high as 9.8. But then, due to air resistance, it is reducing his acceleration. And that's essentially what the parachute is doing, is reducing his acceleration to a point where it can achieve a maximum constant velocity, because the acceleration is close to 0, which means there's 0 change in velocity. Okay, as time changes. Ashley. Velocity time graph, almost like a parabola, it's actually an exponential curve. It exponentially approaches an asymptote. Yep. Okay, so when you're in maths methods, when you look at exponential functions in semester 2 of maths methods, then you will examine the shape of those types of graphs in more detail. Okay? Very good. Any other questions? Alright, so air resistance can be quite complex behavior of motion, but it is, you interpret it as when the skydiver is close to its terminal velocity, that means he's now traveling at a constant velocity and it's no longer accelerating as an overall acceleration of 0 meters per second or very, very close to it. Okay, when the skydiver is close to its terminal velocity. Okay. Nicely done. So for what we're going to continue on in this lesson, we want to now extend our ideas to motion of an object on an inclined plane. We're going to cover look at the forces acting on an object in the inclined plane and determine the net force, and then determine the acceleration. Okay? And we're going to examine that as an experiment also on Thursday. And you've got two options for your experiment. You can look at one involving a falling object, okay, and then another looking at an object moving down an inclined plane. But what I'm going to get you to do, what I need you to organise for yourself for our experiment on Thursday, is to bring a device, electronic device like a mobile, that is able to capture video and able to film it, okay? And bring your Chromebooks as well, because we're going to analyse the film of the motion and use what's called a video tracker software to measure the position and the distance travelled by an object over time. Okay? So you need your mobile, you need your Chromebooks, and you need a video tracker software. At the end of this session, I'll point you to the software as an app that I want you to download and get ready and organised for Thursday.
Different city, a
Okay.
different club. This is Perth, and I played at the Air nightclub.
Now,
From one music level to another. This is Go On Air, live from Club Air, Perth.
okay. Yep, that's right. So what we'll do before we commence and get into our inclined plane, what I want to bring you towards on your Google Classroom is a number of force problems that requires you to look at the diagram, and you have to redraw each picture and label all the forces acting on the mass in the same way we had done last lesson. Okay, once you've labelled all the forces acting on the mass, the next step is we're going to first determine the overall net force. Okay, and then we're going to relate that to the acceleration. Okay, so we want to be able to determine what will be an acceleration of an object experiencing such forces. Alright, so you can bring that task up by going to your Google Classroom, start off with. And then I'm going to start you off by, we're going to do the first 2 or 3 together, and then I'll get you to do the rest as a homework task. There's only 6 questions. Yes, please. Okay, so the first one, who can describe one force that we know for certain that's acting on the crate? An applied force, very good. So we've got an applied force here. That is a pushing force heading downwards in that direction. And what's important, it's acting actually at an angle theta compared to the horizontal or the ground level. So there's the ground level. All right, you need some perspective, you need to have some level that you could say, okay, this force is at an angle relative to such level. In that case, it might be ground or horizontal. Okay, so it's important to note that this is a force at an angle, and the angle in this case in this problem is 30 degrees, at an angle of 30 degrees. Now, that is 30 degrees to the horizontal. Alright, very good. And its size is how much? 20 newtons in size. Okay, so we've got a 20 Newton force at this 30 degrees angle to the horizontal. Alright, what's another force that we know would occur on this crate? Yep, force due to friction, but generally in most real world examples, absolutely friction is very important, but this is a more simple example and it says we're told that it's frictionless. So you've got to look out keywords in this information, such as where it spares us one other force to consider. Force due to gravity, where the crate interacts with the earth. Yep, so, and what was the other one, Zach? The ground pushing up on the box. Very good. So there's one force, the force that is directed vertically downwards. This is where the crate is interacting with the earth under gravity. What do we call this force? Weight force. And it depends on G, Mitchell. Very good. So weight force W. Who remembers the little calculation you would do to work out the size of the weight force? Mass multiplied by G, gravity. The acceleration due to gravity. Mass times G. Okay? Now, because this is all on scenarios focused on, Earth, we know that on Earth the strength of gravity is 9.8 meters per second squared. Now, and then we've got this force where the ground pushes back up on the crate. Okay? What do we call this force? The normal reaction force. Yep. 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 And look, just for importance sake, look how I've drawn my forces from. On the crate, I've taken right in the middle as the position where I've drawn my weight force, okay? Because the forces due to gravity, it's an interaction between objects of mass, okay? Just like the Coulomb force when we looked at charged particles, yeah, and the electrostatic attraction and repulsion of forces, that is an interaction between charges, a positive charge or negative charge, okay? But gravity is a force between masses, and masses of a different size, different shapes, but you can identify one point called the center of mass as a representative point for the origins of such a force, okay? So the force due to gravity you could say, originates from the center of mass and pulls towards the Earth, and more precisely the center mass of Earth, which is right down in the origin or the center of the Earth. Okay, the core. Now the normal reaction force, it has an important job to do as well. Its job in this case is to support the box from having an overall acceleration down towards the center of the Earth. Such as if the ground wasn't there and you were pushing it off a cliff, there's no supporting force underneath the box. And so what it's going to do is fall towards what we perceive as the ground, but what it's really trying to fall towards is the center of the Earth. And it's only by luck that, most things encounter hard ground before they get to the center of the Earth. Yeah? And it's the sudden experience of this normal reaction force when it hits the ground that creates a huge impact. Normal reaction force? That's a very good question, but this reaction force is not reacting to this force due to gravity. Okay? And this guy, let's draw him in a different color so we can realize what's going on. This one there is a reaction force due to Newton's third law. Okay? But it's a twin, but of another force, but not of the weight force. Okay? It's the evil twin of the contact force that the crate makes with the ground, which is this one. Okay? This one, though, is the contact force that the crate is pushing onto the ground. This is the force from the crate onto the ground. Okay? And then the ground reacts to that and say, hey, you're going to push me around, I'm going to push you back. Yeah? And it does exactly that. It applies a reaction force back onto the crate. Okay? Yes? Yep. Undefined. It will be potentially infinite. Yeah, but it's undefined because no one actually is being able to prove that experimentally. But mathematically, the amount of the force, the size of the gravitational force, yeah, would go towards infinity. Does that make sense? Very good question. And we'll look at that a bit later on in semester 2. Alright. Now, the one we're interested in are only the forces acting on the crate. So, this one that I'm erasing was only acting on the ground. Okay? We're not interested in the acceleration of the ground because, as we know from our experience, it doesn't move very much. It's always there. That's because, why? It's experiencing a force as well, but it's not accelerating. How come? because it's too big. The mass is monstrous compared to the size of a crate and the size of a force. So the acceleration is minimal. Yeah? Alright, so we've identified our forces. Now what to do about this guy, this force on an angle? Okay? So when you examine all the forces in what's called a free body diagram, I'm going to represent the crate without a body, without an object. It's just going to be a dot. And that dot is representing the center of its mass. That is this dot right there. Okay? So all of the forces now acting on this crate without a body, it's the weight force, it's normal reaction force, and it's a pushing force of 20 newtons at an angle of 30 degrees to the horizontal. Yep, but the good thing about force is what kind of quantity? Vector quantity, very good. What are the two important properties of a vector quantity? Size of the quantity and the direction of the quantity. What about the position of the arrow? Does that matter? Not really. It's only the size of the arrow and the direction that the arrow is pointing. That's all that matters in a vector. That means I can put the arrow in any position on my diagram. As long as I've got the same size, correct, and the direction correct. Yeah, that means I can start it even. Doesn't have to start from the bottom, the ground. I can start it from the center of mass, because it's still pointing up of a size n. Okay. Now, if I'm trying to find the net force, okay, what I want to be able to do is think about all the forces that are acting in the same direction, the same straight line direction. So that's what I have to ask myself. What are the size of the forces in the same straight line direction? Okay, how many, looking at the forces that we do have, how many different straight line directions could we possibly have? Well, we've definitely got an up and down straight line direction. You everyone see that? So we've got forces acting just perfectly in a vertical straight line direction. We've got this one on an angle, sure, but every force on an angle can then be broken down into a vertical part and a horizontal part. Okay, now these are called components. So we've got a horizontal and a vertical component. Now, what do you think we would have to do to figure out the actual equivalent size of these component forces? In terms of to make them appropriate equivalent in size to the 20 newtons that's on an angle. Okay? So if you look at the geometry, the shape that was constructed, you can see really they belong to a right angle triangle of forces. So if you've got 20 newtons on an angle, then its vertical component, the one that goes down, all right, which is a step. If you want to go 20 newtons that way, we can go so many newtons down and then so many newtons across, and we end up in the same equivalent spot. Yeah? Then what kind of geometry or mathematics do you think we'll have to draw on to figure out the size? Trigonometry. Absolutely, trigonometry. And you've got to recognize that I've got a opposite side to an angle, an adjacent side to an angle, and a hypotenuse side to the angle. And if I want to use my trigonometry, then I've got my trig ratios. Yep. I could use sine. Yep. So that means the sine of the angle has to be the same as the opposite side over the hypotenuse side. So if I'm interested in the size of this vertical component force, this opposite side of the triangle, then the opposite will be given by the denominator multiplies over to the right, the hypotenuse multiplied by sine of the angle. Yeah? Now, what would be an equivalent calculation to work out the adjacent side of the triangle, or the horizontal component of the force? 20 times sine for the adjacent side. Which trig ratio relates to the adjacent side of the triangle? The cosine. Because sok, ka, toa. Ka means cosine with the adjacent and the hypotenuse. Yeah, you learned this in year 10. Yeah? I hope so. Then why are you making mistakes? Okay, so we got to use the cosine ratio. Alright, so they're our important things. So let's look at our two overall now. You can break this down into two versions of the net force. Okay, we get two versions of the net force. We get what's called a horizontal net force, or a parallel to the motion net force. So our horizontal net force, which is the net force is denoted like that, okay? Let's identify all the parts that are just traveling horizontally to the motion, to our diagram. Now, this one there is vertical, that one there is vertical, this one over here is vertical. There's only got one part of the net force that is horizontal. That's this one running across. Now, let's use trigonometry to work out the size. The horizontal is 20 newtons, the angle is 30, so it should be, the adjacent side is found by taking the horizontal amount, the actual size of the force, the 20, multiplied by cos of angle 30 degrees. Like so. Okay? And that gives you the size of the net force. That is the net force. Okay? Now, the net force in the horizontal direction, remember what Newton's second law said? That the net force is the same as the mass multiplied by the acceleration. Okay? So if you can work out the net force, then you equate that to the mass of the crate multiplied by the acceleration of the crate. Now, if you think about this situation logically, which way is the crate likely to accelerate or start to move? Forward, horizontally. So overall, we're going to get an acceleration in this direction. Isn't that right? Now, that's the horizontal direction, which is the same direction as the horizontal part of the pushing force. Does that make sense? So this net force is equal to the mass of the crate multiplied by the acceleration that it's going to experience. Now, is there any acceleration in a different direction? Say for instance, could the crate accelerate due to the vertical forces? They're balancing. What are they balancing now? Yeah? It's only affected horizontally. And we know it is because the crate will only move horizontally along the ground. It's not, if we push something at this angle, it's not going to automatically travel downwards into the ground or spring up into the air. So there's no vertical direction or acceleration at an angle. Friction will add to the size of this acceleration by holding it back. Yep. So, if we to now consider the vertical net force, okay, then we want to add up all the forces by looking at the diagram, looking at the forces we've drawn that are going in the vertical direction. So, we've got one force called the normal reaction force that goes up. We've got another force called the weight force that goes down. Notice how they're in opposite directions. What do we have to write down to account for that? We've got to subtract one of them. Okay, so we might have the normal force going up might be positive, but then we're going to subtract the weight force. Okay, and instead of writing W for weight force, we've got a helpful little formula which can help us calculate the weight force in terms of other things, where weight force is mass multiplied by 9.8. Alright, so the weight force is mass multiplied by 9.8. Good. Now, is there another force? Is there another force also that's going in the vertical direction? This one here is this component. It's the vertical component of this 20 newtons that's on an angle. So, look, it is pointing downwards, okay, towards the ground. So, we said that the weight force going downwards was to be subtracted, to have a minus. So, we also have to account for this one. So, we're going to minus, okay, this size of this opposite component of this 20 newtons force on an angle. So that opposite side is worked out by hypotenuse multiplied by sine of the angle. So the hypotenuse is the 20 newtons that is multiplied by sine of 30 degrees. Okay, which is 10. Very good. Now, altogether, what should we expect to be the overall size of this net force in the vertical direction? 0, absolutely. It has to be 0, yeah? Because there's no acceleration in this vertical direction. This acceleration here that it's actually going to experience is only horizontal. there's no part of this that is popping up on an angle like that, because we know that the crate, when pushed along the ground, isn't going to, naturally, it doesn't fly up into the air. Yeah? So you say that because it's got a 0 vertical acceleration, it's got a 0 net force. So all that is equivalent to a 0. Alright? So those are the 1, 2, 3 forces in size that are going to be balancing each other out. Does that make sense? These forces balance. So the only force we don't know in size is what's going to be the actual size of the normal reaction force. And because we know that they are going to balance, we can easily work that out by calculating that, and adding it to the other side of the 0, and we get the size of the normal reaction force. Does that make sense? And that's how big this reaction needs to be to balance out the situation. Now, so the most important part is the goal of the problem. We're told to actually find the acceleration that it experiences. And the only part that is causing the acceleration is the horizontal part of the force. Okay? And so that means our 20 times cos of 30 multiplied by mass times acceleration from Newton's second law. So then the actual acceleration we'll calculate as 20 times the cos of 30 degrees, and then we have to remember to divide by the mass to work out the acceleration. And the mass is, there we go, 20 kilograms. And you can see 20 is going to divide 20, so it's just the cos of 30 degrees, which is about 0.87 meters per second squared in size. Okay? And that's the actual acceleration that the crate will experience horizontally. Sorry? No, not really.
So if there was friction, would we subtract it?
Absolutely. If there was friction, we would have to subtract that friction. And you'd subtract the friction in the horizontal net force part. Okay? Very good question. So the goal of these problems is to be able to break down our forces into 2 straight line directions. They are horizontal direction and then a vertical direction. And what you have to do is, for any force that's acting on an angle, you've got to recognize that every force on an angle is like the hypotenuse of a triangle. And you work out its components, being a vertical component, a horizontal component, using trigonometry, using the hypotenuse times sine of the angle to get the vertical part, or hypotenuse times cos of the angle to get the horizontal part. Does that make sense? Yep. Okay. Now, one more. The first one was more complex and harder. The second one, a lot more straightforward. Okay, so a water bottle of 750 grams in mass is sitting stationary on a table. What does that mean, sitting stationary on a table? It's just sitting there, it's motionless, it's not moving.
Hope you're enjoying today's Go On Air.
So, in terms of a quantity of motion, what could we say that stationary would mean? Zero speed. So it has good, it's got a velocity of 0. Yeah? V is 0. What else could we say? Because it's just sitting there and the speed of 0 is not changing, it's staying 0. All forces are balanced. And that means also the acceleration is 0. Okay? So that's what we get. That's the information we get from an object being stationary. Does that make sense? Calculate the size of the normal reaction force that the table exerts back onto the bottle. Okay, so we think about what are the forces acting on this bottle. We've got one force pushing vertically downwards. What's this one? Weight force. Mass times gravity. Okay, now, and then there's another force that is acting on the bottle, and that's the normal reaction force of the table pushing back up on the bottle. That's our N. And the job is to find the size of that force. Are there any other forces acting on the bottle? If it was pushed like this, horizontally, yeah, then you might get a pushing force going this way, and then there will be a little friction force trying to counteract that. Yeah. Maybe wind, yeah, but you know, there's no wind. Alright, so in this example, those are the only two forces, and they're all vertical, yeah? So we can add them up in the net force. So we work out what is the overall net force, and they're all acting in the vertical direction, but because they're in opposite directions to each other, you've got to remind yourself, what do you have to do when you're combining those forces? You've got to subtract one of them. And to help you to decide which one to subtract, what you can do is label on your diagram directions. So I could say, if I'm traveling up this way, that is the positive direction. If I'm going down, that's the negative direction. Yeah? But if I'm traveling horizontally, if it was a two-dimensional scenario, then that way might be positive. If I'm going the other direction, that way might be negative. Does that make sense? How am I going to write my net force expression? What would I write? Which one am I going to subtract? The normal reaction force or the weight? I should subtract the weight force. So I'll have normal reaction force minus the weight force. Very good. And we know something about the weight force, so we're going to use its little formula. Normal reaction force minus the mass multiplied by the gravity, acceleration. Now, what else do we know about the net force? Overall, what should that be equivalent to? 0. Very good, because it's stationary and the acceleration is 0. Because it's stationary. Doesn't matter. Doesn't matter. Yep. It's what you decide. Okay, so then if normal minus the weight force is equal to 0, then what would the size of the normal reaction force be equal to? The weight force, same as the weight, which is the mass multiplied by gravity. And that's what we can now use to calculate the size of this force. So what is the mass of this bottle? Now, 750 grams, but what's the most appropriate unit for mass to be able to calculate the force in newtons? It's got to be in kg, all right? Because what's important to realize, 1 newton of force is equivalent to 1 kilogram multiplied by 1 meter per second squared. Okay? So we've got 0.75 kg times 9.81 meter per second squared. And that gives you your overall normal reaction force. What did you get, Lachlan? 7.35, very good. 7.4 newtons. as the size of our normal reaction force. Everybody understand? Alright, so that there gives two examples of these kinds of problems. One involving a force at an angle, and the second one involving this idea of forces balancing out when an object is stationary. So what I'm going to get you to do is now, I want you to have a look at question number 3 on that Google Classroom task. Try it in your book. I'm going to come around and assist you and give you ideas and advice on how to approach it. We've got our inclined plane. We've identified what forces are acting on the mass. We've represented those forces in a free body diagram. Now, what's important now is thinking about can we categorize each of those forces into either one that is parallel or horizontal to motion, or perpendicular or vertical to motion. Now, motion, Aneth, what is indicating the right direction of motion in our diagram? It's going up, that's the acceleration. So this part, the blue arrow showing the direction of motion. So something that is parallel to the direction of motion is running along the same side of it, isn't that right? So this way is parallel to motion. And if we're running this way to parallel to motion, who can name the forces that are also parallel to motion? An applied force, very good to me. What's another force that's parallel to motion? Force due to friction, very good. Okay? Now, what about perpendicular? Perpendicular to the direction of motion. That means, what angle is perpendicular coming out? 90 degrees coming out. There we go. So, that part there now is a perpendicular part to the direction of motion. Which force could be categorized as being perpendicular to motion? Normal reaction force, very good. Now, which force haven't we included? The weight force, yeah? So far the weight force doesn't fit as being parallel to the direction of motion or perpendicular to the direction of motion.
That's horizontal. Hey, what do you mean, man? Yeah, that's
now. But what's important here is that we're going to break it down into its components, into its parts. Okay, and this is the important point highlighted in this red sentence. Forces on an angle can be broken down into components. Does that make sense? So, our weight force, we want to have one component that is perpendicular and one component is parallel. So for it to be perpendicular, one part has to come out this way. And you can see that now is in a straight line with the normal reaction force. And that means it's perpendicular to the direction of motion. Yeah? And then the other part has to run down parallel to motion. And it makes this right angle triangle. Can everyone see that? So this weight force has to be broken down into parallel and perpendicular parts. And now, one part of it will fit in the parallel category of forces, and the other part will fit in the perpendicular category of forces. Now, the question is, the inclined plane depends on an acute angle theta, yeah? And the right angle triangle we've made on the parts of the weight force also has an acute angle theta. But is the equivalent acute angle, is it down here in the right angle triangle, or is the equivalent acute angle theta up here in the right angle triangle? Where do you think it should be?
Up there.
Up there, absolutely. So it is that then produces your right angle triangle for your weight force. So when we rearrange it, there's your weight force, there's angle theta. So then you can identify which side is the opposite side on the triangle, which side is the adjacent side, and you figure out whether you're using a sine theta factor or a cos theta factor. Okay, so what we want to do now next is, what would the net force become? Okay, so I'm going to leave those little challenge for homework, and we're going to review it in our very next class. What will be the net forces acting on this mass in this inclined plane?